Right. Last lesson, we talked about gravitational potential energy. Right? And we gave you the idea behind it. Some students came to me afterwards and said that they are not sure about how I got it, right? Just know the definition is fine. Right? If you are not too sure how I eventually derived this, please revisit your work energy power lectures and tutorials. Right? It's actually based on that. Okay? So at this point, I don't need you to know that too much, but I need you to memorize and know the formula at least. Okay, so at this stage is U equals to negative GMM over R, and we let the GP be represented by U. I've given you this graph, yes? Right? So I also explained to you last week how we resolve, how we think about GPE, and how we think about GPE in celestial systems in gravity. The difference? Hey, hurry up. Shh, quiet. Okay, so this is the alignment, right? Because in our common picture of GPE, we say that when we drop something, we move something higher up, it has a higher GPE. So here, I want you to notice the language very carefully. When we talk about GPE at infinity to be 0, it is still true, just that the number becomes less negative. A number that becomes less negative means it's a larger number, and hence it's a higher GPE. Correct? Alright? So you need to know that. Okay, and this leaves us with this is that U is a negative sign, right? Means that we are bounded to Earth. Right? It's attractive nature due to the forces, and then we are bounded to Earth, and we are taking 0 as the reference. Okay, so example 10, they ask you to find the GP at A, B, and C. That is not difficult. I'm just going to show you the answers because it's just a direct application of the equation. Okay? It's a direct application of the equation. Part B. Show that if H is very, very small compared to R, right, the double arrow is very, very small compared to R. Show that the change in GP going from A to B is approximately MGH, which is... So this question is very good because it's trying to show you that GPE can be approximated by MGH, where G is the G at the surface of the Earth, right? So part B, the change in potential energy from A to B is the energy of B minus energy of A. The math becomes a monster. Right? You need to copy the first line here. And I want you to notice the negative sign. So U of B is negative minus the U of A, which is also negative in question. Then you can see that common factors can be taken out and you get this. So I need you just to copy the first line. And here is the math. So I need to explain this a little bit carefully. From here, which on your page is the column on the right, and the curly sign to approximate it. Why is it that we can do this? It's because a very, very large number plus a number that is very small compared to it might as well just be the very large number by itself. Okay? So we can just ignore the h at the bottom. Then, if you look at this equation, Gm over r squared is just your gravitational field strength, and observe is on the surface of the Earth. Because this r is the radius of the Earth. You need to be very, very careful about that. Okay? This g, this mg, small g, is not a variable, it's a constant. It's 9.81. Next, part C. So what's the minimum energy for an object at A to go to infinity and never to return? Right? So the counterpoint is this, right? It's like if I throw my wallet up, it comes back to Earth because I have not given it enough energy to go to infinity. Right? So what energy is it? Well, the energy will be the difference in the potential energy, 0 minus the energy on the surface of Earth, which gives you this value. And I want you to remember this value, right? Or these symbols, because this is the energy that you must give in various forms to overcome the gravitational potential energy. To give you an analogy, it goes like this. If you are you are in a well, you know what a well is, right? Because you all get your water from a tap, right? You don't get it from a well. Do you know what wells are? Okay, context, right? So you're in a well, 10 meters deep. How much GPE do you need to get out of the well? The GPE will be your mass times G times 10 meters, right? So you need to have a KE of at least that value. Do you agree? To convert to the GPE. You agree, right? Great, because then that brings us to the next page of escape speed. Because the energy that I gave you of escaping that well, that physical well of 10 meters, is the same as escaping the gravitational potential well of Earth. Right? You must have sufficient KE to convert away to GPE and not return. And this must be the relationship between them. Your KE must be larger than the GMM over R that you have found in example 10. Right, so this GMM over R is actually from example 10. Okay? That means the K you must give an object must be the GPE is the positive, the magnitude of GP that it has at that surface of the planet, whichever planet it is. Okay. Rearranging. Oh, okay. So just read the words. The initial K percent must be more than the equal sign people can understand, but why more than? Okay. So to explain this, I explain what it is less than. If your half mv squared is less than this, what will happen? You'll reach a certain point very far away from Earth, but still not at infinity. And then the K will reach 0. Correct? You put it up, the K will reduce from 100 to 99 to 0. But your GPE is still at -1. So what will happen? You get attracted back to Earth. So you have not escaped. Why your mv squared must be larger is such that when you reach infinity, when your GP has become 0 or very, 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 very tiny amount, you still have a K that is much larger than it, you have literally escaped to infinity. Also, we are not talking about physically reaching infinity, we are talking about the energy being able to reach infinity. Okay? Can? Right, so the Acid speed is thus this. Okay, this is given to you. And for context, Earth's escape speed is 11.2 kilometers per second. Is that fast? It's not kilometer per hour, friends. It's kilometers per second. If it's kilometer per hour, you have all escaped already. That means when you drive a car, you go out of space. And never to return. Okay? Escape speed. So, good and bad. I give you two reasons why it's good. I give you one reason why it's good. If the escape speed was lower, for example, for Mars or for the Moon, the escape speed is very low. It's around 500 meters per second only. The moment the sun shines on the moon, whatever atmosphere that's on the moon gets heated up and can escape to infinity. Right? So having a high escape speed is relatively good because it allows the atmosphere to be retained on Earth. Right? You find that for the same temperature, you'll learn later on, for the same temperature, molecules of different masses, helium, compared to oxygen, will have a higher speed at the same temperature. Which means that helium is more likely to escape Earth than not. Which is why there is a crisis, crisis of lack of helium. Helium, because a lot of helium balloon raises up, go to the atmosphere, explode, and pop. And all the helium is higher in the atmosphere. The sun shines on it, it has enough energy to escape Earth. So the amount of helium on Earth is decreasing. And helium, we know, is very important for medical research and medical surgeries. So that's that problem. And of course, for balloons and for funny sounds. Okay, wait. So I said, this is a good thing, but it's also a bad thing. Why? We cannot escape Earth, that's right. Because this speed is so high, we are not able to explore space easily. Okay, so it's a good and it's a bad. But okay, that's life. Okay. Moving on. Let me talk about gravitational potential. Gravitational potential, I need your 100% attention because every year when I reach this, and after I finish the lecture, I ask the students, you know what is gravitational potential? They'll be like, yes. Very uncertain. So I'm going to give you an analogy now. Gravitational potential is like a hill. You think of it like the contours of the hill. The higher you are on the hill, the higher potential you have. So later I'm going to show you a graph of potential. You think of it like the slope of the hill. If I place a ball right at the top of the hill, it will not roll anywhere because it's at the top where the gradient is 0. But if I tip it a bit to the right, it will roll down. If I tip it a bit to the left, it will roll down. Potential has the same concept. The analogy to our physical understanding, right, is a shape of the hill. Okay? So now let's talk about potential. The definition of gravitational potential comes from this equation. Okay, that I'm circling now. Okay? The gravitational potential at a point is the work done per unit mass by an external agent in bringing an object from infinity to that point. You notice that the definition is very similar to that of gravitational potential energy. The only difference is the per unit mass. So we are using GPE to define potential. Okay? The equation is given as such. Alright. And it is in nature to go to the lowest potential energy. Right? All objects tends towards lower potential energy. Okay. So, everything else is given, the equation has been done. The graph will look like this, obviously. And for a certain position of r from the Earth, you get a fixed value. So again, conventions, small r is the variable, big R is the fixed value. Okay. So at this point, it makes sense to talk about what is equipotential lines, right? I said in the first lecture, I will tell you that. So this is a very good juncture to explain what it is. So this is my repetition. If you place a ball here, right, it will roll inwards. And as it rolls inwards, it gets faster and faster and faster. Okay? Right, equipotential lines. Right, equipotential lines are lines where everywhere on that point has the same potential. So everywhere on this red line now has the same potential. Everywhere on the orange line has the same potential. Okay, these are called the equipotential lines. And you need to learn that equipotential lines are always perpendicular to field lines. Okay, equipotential lines are always perpendicular to field lines. So if I ask you now, the field lines around me, can you imagine which direction they point? They point downwards and equally spaced apart. So my equipotential lines will look like what? Will be here, 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 which is actually the height. Right? I can draw an equipotential line here, which is maybe 1 meter tall. I can draw another one here, which is 1.5 meter tall. So the equipotential line is the analogy is the height. Right? It's the height of a contour of the slope. Okay? Right, and this is the important point. Right? Addition of potential. This is also one part that a few years ago when I lectured, people were like, what? So I'm going to spend more time on this. There are two planets A and B. Let P be a point between the two planets. Right, on a line between the two planets. Okay? If at point P, the potential due to A is -2, and the rest, and the potential due to planet B is -3, the total potential at P must be -5. It's just a simple addition. Okay? It is like that, but I need to state it explicitly and clearly. Which then allows us to say this. I can then choose another point away from P, right? And if due to A is -3 and due to B is -5, the total will become -8. Okay? Which allows us to draw the following graphs. The red one is A, and you see this is the potential line due to A. Remember, on page 11, I drawn for you that graph. I can draw another one for B, which goes this way. Does it make sense to you? For B, the blue one, it goes this way. Does it make sense for you? You will notice two things. One, B, the value is bigger. The value is more negative. I'll be very careful. It's more negative than the value at the surface of A. Why? Because B is more massive, more dense, so and so forth, whatever. You get this. Okay? You notice that they intersect at a certain point. And you notice that the resultant, the maximum, is not at the intersection. One of the common misconceptions of students is they think that at the intersection is where the maximum resultant potential is. It's not true. right? It is at the point where the increase in potential of B with distance is equal to the decrease in potential of A with distance. Okay, that means the change of potential with distance must be equal. Okay, you will see that why later on. Right? So if you look at the gradient here, the blue gradient here, and the red gradient here, one is negative, one is positive, but the magnitudes are about the same. That's where the maximum resultant will be. Okay, and that's the point where if you place an object there, it will not move because the potential gradient is 0. Okay? But my point for this slide is to how to add it together. Any questions now on how to add potentials together? I give you 2 minutes to discuss with your friends. Okay, go. Okay. Any questions? About who is that? Can you raise your hand? Oh, which part? From where? Okay. If that's what you are not sure of, we will talk about it later on. Yes. If you are interested, I can point you towards page 16. Why is that the maximum? It's because the change of potential with distance becomes 0, means the G field at that point will become 0. Okay, I'll talk about that soon. Okay. But if you want to have another, I try to give you something. Okay, since you asked that question, you may have I try to give you something. If you move to your right and you add a height of +2, right? You move to your right and you add a height of +2, and your friend moved to the left and decrease the height of +2. That total change at the point is 0, is where the total value will not change. Okay, one more time. One more time. Okay, I get it. Okay. First I must say this is a slightly minor point in the whole of gravitation. I'm not sure if, okay, you're LT3, so you've got more time. The point of equal, where they are equal, is actually not the point of maximum potential, resultant potential. Why? Because you see, look at the red graph. Is the gradient steeper in terms of magnitude compared to the blue graph? Is it? Yes. If I move to the right, see where my cursor go? Did I increase my potential of A by a lot more than I decrease the potential of the blue? Which means the total value must go up. Do you agree? So, you must find the point where the increase of the red when you move a short distance is equal to the decrease of the blue by a short distance. And that will be where the gradients are equal in magnitude. Okay? Okay. Oof. Yes. Alright. We're going to talk about this a little bit more now. Knowing the potential at the point. So I ask you, I'm going to point to this space. Look where my finger is. This exact point. Is there a potential here? Yes. Because there's Earth, there's a potential here. Is there potential energy here? You cannot talk about potential energy of nothing. Now I place my handphone here. Is there a potential energy of my phone? Yes. Any mass you place in a potential will have a potential energy. You need to now know the difference. A potential is a space due to a bigger mass, and you place a mass there, then this mass will have potential energy. Okay, so now let's do. This is the resultant gravitational potential distance graph between the moon and the Earth. The axes are negative 1.3. Look at the potential. 10 to the power of 6. 10 to the power of 6 joules per kg. So these are one of the oldest tricks in the book for physics exams. They have a power in the axis. Please remember. Okay. Right, so the first question. A rock of mass 1 kg falls from point P towards the surface of moon. What potential energy does it lose?
Is it joules per kilo or just joules?
Joules per kilo.
Because here is just joules.
Joules per kilo. Right, so that is for you to fill in. Very good. The axis there is for you to fill in. Thank you, Matthew. You saved the whole. It was on purpose, right? Obviously. Thanks, Matthew. All right. So you are supposed to fall from negative 1.3 to negative 3.9. What energy does it lose? Okay. So, A. The loss in GPE is a change in GPE. Will be the energy at point P, the potential energy at point P minus the potential energy at point M. But potential energy is given by mass times the potential, mass times the potential. Then you get this. Okay? Because you have already given, it's a mass of 1 kg, the mass is 1. I plug in the values of the potential and times 10 to the power 6 and get this value. Okay? This is kind of important. Not kind of. This is important. This is expected for you as a student in any test or exams. Okay. Then they ask you, what is the speed of impact? If this is the loss in GPE, assuming no other resistive forces, this will all become KE. Right? So this part is not difficult at all. Okay, immediately sub this in, I get my answer. So part C, I want you to try. Once you have copied part B, I want to give you 2 minutes to try for part C. Okay, if you were now to fall from P to Earth instead, what would be the speed of impact? eventually. But if you don't know now, you need to, I give you a clue, it's the same as part A and B. You just change one value. I only got 15 minutes, so I better hurry up. Okay, right, so I'm just going to show you the answer. It looks like this. Right? The change in potential energy will be the gain in KE. The change in potential is, instead of 1.3 to 3.9, now it becomes 62.3. Okay? So instead of hitting at a low speed, it now hits at a huge velocity. Like that. This, of course, disregards atmospheric friction. Okay? Any question? Those of you who got it, very good. You are engaging your mind and learning. Okay, very good. Yes. Everyone, shh, I need to hear this question. Yes. Will it fall to earth and fall back? Oh, why would it fall to the earth or to the moon? Very good question. If you are at point P, you wouldn't fall. But a point is, in theory, just one very small point. So if you have any slight perturbation to go to any side at all, it will start to get faster and faster and faster to that side. It's like you're on a slope which is curved without any flat plateau. There's no flat plateau to place the. It's not like a table. It's like trying to balance a ball on my water bottle. Here, it cannot. Well, it's hard. There's one point, but that point is so minute, so it will fall. Yeah. But whether to the earth or to the moon, who knows? Okay. Any other question? Okay, I hope you're hanging on. Let's now go to the orbital energies. Remember, point 3 of my notes is about all the orbits, right? All the orbits. We talk about the velocity, the period, the distance. Now we're going to talk about all the energies. And here, before we start, I need to clarify this. Orbital energies are for things that are doing orbits. If I throw my wallet up to infinity, is that an orbital energy? No, that's a projection kind of energy, not the same thing. Can you write it down clearly? Orbital energy is not the same as I throw something up towards the sky. It's not the same. Orbital energy is for something that is orbiting. Okay? Why? Because misconception again, many students confuse the two and don't know what's going on. Also, you need to make this mental structure in your brain. It's not the same. It's not a simple conversion of energy question. Right, so let's start. For any energy, for any satellite that is orbiting, the total energy must be the sum of the GPE and the KE. K will always be a positive value, but potential energy will always be a 0 or smaller value, right? So you have this equation. They're like, how to combine it together? Can or not? Can or not? Answer is actually can. Because if you look at the previous chapter, you have expressed V in terms of all these symbols. Right? So this is a recap. Since the gravitational force provides for the centripetal force, you can rearrange to get mv squared equals to this. Then you sub in. The kinetic energy is equals to gmm over 2r. Can you see? And I now want you to compare what I'm circling. The energy for the potential energy and the energy for the kinetic energy. What can you say about them? The signs are different. One is negative, one is positive. What about the magnitude? The kinetic energy is always half of that of the magnitude of the potential energy. Which means the total energy is what? The total energy must be exactly half of the total energy because you have -1 plus half. Do you agree? If this account, all of the potential energy account is -1, the kinetic energy is actually plus half. Do you agree? So the total energy is plus half minus 1, which gives you minus half. Also, you have half minus 1 gives you this, minus half. Okay? Which then allows us to draw certain things. But first, there's a chunk of text. The minus sign shows that the energy in the Earth satellite system is a closed one. That means the satellite is bounded to Earth. Right? You need an external source to tear away from Earth. Right, so what do you have? Watch, When you draw this, just start with the potential energy graph. This one does not change. For any mass, this will be the potential energy graph that you have. Then, I want you to watch this carefully. Oops. Can you see? I want you to indicate when you are drawing it. Listen, listen. The dotted lines, why is it there? Can you see that the dotted line here, this space where my cursor is moving up and down, is half of the space of this line below? And the same thing here. This is one size, this is twice of it. Can? And the total energy is just the reflection of the kinetic energy graph. The E graph is just a reflection of the K graph. So these are your three energies that you have for anything that's doing an orbit. Okay? So in your tutorial, there will be one question that addresses this. I'm talking about a satellite that's orbiting Earth, encounters some air resistance, it loses a little bit of total energy. What happens to it? If you lose a little bit of total energy, you will spiral closer to Earth at a smaller radius. You will lose GPE and you will gain KE. I say again. So if you have a satellite that's spiraling initially at this radius where my cursor is moving up and down, if it encounters some air resistance, it will lose total energy, which means you will go inwards to a smaller radius. It will actually lose GPE and gain KE. So you're spiraling in faster and faster. Okay? Right. Ooh, now this is the one. This is also something that was not previously in the in previous gravitation, but I personally point it out because a lot of students don't know. And this is now, we're talking about all the joints. This is actually from work energy power. The gravitational force is related to the negative of the potential energy gradient. This is a fact. F-A-C-T is a fact. Okay? So what does this mean? So now let's try to understand this mathematical symbol. Okay? That means if I give you a potential, a UR graph. Oh, okay. These are the two things I need you to do. Okay? The one on top is on page 16, the first few lines, right? It's the negative of the potential energy gradient. And the one below here is for part B, right? Halfway down the page. I added in the graphs because a lot of students were so confused, so I like to state it explicitly, right? Right, got time? Got, let's go. So, first one, F equals negative du dr. If you are given a UR graph, it means that the gradient on the UR graph, you draw a tangent, right? This tangent at this point gives you a positive gradient. But you multiply in a negative sign, you get the value of the gravitational force, which is negative in nature because it's attractive. Okay? Hence, it's the negative value of the force. So the UR gradient is the negative value of the force. So this is on the first graph, first box that you have on the left hand side. Can? One more time now, the order of sequence that came out was this. You have a UR graph. I find a gradient at a point. I'm finding the value of the F here, indicated by the golden arrow. Right? So the gradient is a negative value of the force, which means the negative of the gradient is the value of the force at that point. Can. Okay, I'm going slower for the first half of the page because if you get the first half, the second half is easy stuff. But must know. No? U equals to du dr. Du dr is just gradient. Yes, question? I heard a big huh. Yes, boy, I'm looking at you, yes? No? Okay, next one. So the second, the right column, if you are then given a FR graph, it means that the area under the graph in the orange box is the change in the potential energy. So this orange area is a negative area. If you modulus it, right, you take the positive, you take this, you take the magnitude of it, it will be the increase in R. Because the area under the force distance graph is work done. Work done is an energy. It must have added to the potential energy of the system, whichever system it is. Okay? So the area under the FR graph is the change in potential energy. So this relationship we are talking about, F equals to negative du dr, that we have been talking about for the last few slides, it helps you to decide, given whichever graph, what to do next, right? If given the FR graph, you can find the change in U. If you're given a UR graph, the energy distance graph, you can find the value of the F. Okay? Question? The next parts are the same. You will notice that the graph looks exactly the same. Okay? For the G equals to negative d phi dr, gravitational field is the change of potential with distance. Look at this. If you are given a phi r graph, the gradient of it is the negative value of the gravitational field. Alright, it's the same thing. Because the mathematical symbols are the same, the analogy will be the same. I only changed from U to phi and F to G by dividing away the mass. Right? F equals to mg, U equals to phi m. This is phi. Right? So it's the same thing. Okay? Yeah, so you're given the phi r graph, you can then deduce the g. So given means the question gives you that lah. Then they will ask you what's the value of g at this point. Okay? Okay, give you a bit more time to copy, which I'm running low of. Okay, can? Right, moving on. If now I give you a GR graph, how gravitational field strength relates with R, the area under the GR graph will be what? The area under GR will be the change in the value of? Change in value of? Potential. Very good. Huh? So one more time, see the animation, watch. It brings it from the higher one to the lower one if you go downwards, if you go from the lower one to the higher one if you take the modulus, right? Can? Okay, so it's basically a change in potential. And you must know whether to add or minus. If you go closer, you must of course minus. If you go upwards, you must of course add. Okay? Ooh. It's not the end, please. It's not the end. Don't back up yet. Okay, so this question is the extension of example 11. State and explain the direction of resultant forces. Right? So all you have to do is to apply what we have done just now. And you can see that if it's to the left of P, the force will point to the left. It's the right of P, it will point to the right. Why? Because to the left of P, the gradient of the potential gradient is positive. Multiplying a negative sign, it means that the value of the G is negative and hence must point to the left because we're taking rightwards as positive. If it is to the right of P, the gradient will be negative. If you then multiply a negative sign with a negative gradient, you get a positive value, which means the G value will be a positive value, which means it must point to the right. Okay? Can? Wait, don't go. I got a lot of good stuff. Summary. To help you remember all the equations. This equation will be given to you. The potential equation will be given to you, but everything else is not. Which makes it so difficult because I heard from my students, we just learned circular motion and that's like already very hard, and now you are throwing me 8 equations. I'm like, yes I am. Right? So I want to help you. So watch, everything above is R squared, everything below is R. Agree? Everything above is a vector, everything below is a scalar. Everything to the left is 2m's, everything to the right is 1m. Everything above is R squared, everything below is R. Everything above is a vector, everything below is a scalar. Okay. Next, everything to the left is 2 m's. Everything to the right is 1 m. Don't go, don't go, still got a lot. Okay, Ken? M and M, the other side is M. That is vector, this is scalar. That's it. Wait. This is also to help you. The left hand side is just the right hand side multiplied by M. You take the right hand side, you multiply by M, you have the left hand side. So with one equation, by right, you can form all the other equations. Okay? This is the method I used when I first started to teach this 10 years ago. I was like, oh, how to remember? I came with a method, and this is the method I use. Has never failed me. Don't go, wait. The one you're waiting for. These are the topics. It will be everything like this. Okay, topics first. Shh. It will be Tuesday, 2 p.m. to 5 p.m. 25 MCQs, 25 marks. 7 compulsory short structured questions. 7 marks and above each. 60 marks. There will be section C, 2 compulsory long structured, 20 marks. Very important. Compulsory, all must do. Wait. Topics, everything except gravitation.